Hello everyone. In today's lecture, I am going to talk about digital to analog, analog to digital conversion and programming AVR for these modes. Before we get to start, if you think about an embedded systems, which is as a digital system, we sometimes need to interact with the outside world to measure a data or to send a data. And if you want to measure or send the data, this data or the devices outside of the embedded system, they can be either in analog or digital forms. So that's why we need digital to analog, analog to digital converters inside of the embedded systems to deal with these analog or digital pulses. So in this chapter, we are going to see this in details. We will cover some of the basics of the digital to analog conversion, the resolution, what kind of modules do we use, and how it's actually making the conversion over there. AVR analog comparator module, which compares two analog values. We'll introduce the transducers, why do we use them, how do we use them, and what's their importance in analog to digital conversion. The major characteristic of the analog to digital conversion, the parameters that we need to consider if you want to configure embedded systems, the linear sensors and their signal conditioning, the discrete ADC modules and ADC in AVR. So we have got registers related with the ADC and how are we going to configure those to perform this analog to digital conversion. So let's give a start and start with the digital to analog basics. Now, when we consider digital to analog conversion, that means on one end, we have got a digital device which sends digital pulses and we need to convert that to analog signals. And maybe we need to send them as an analog to somewhere else. So to do that, we use these DACs or DACs we call it. And generally inside of the DACs or DACs there are two versions of circuitries we can find out. And one of those is binary weighted method of conversion. The other one is R2R ladder conversion. And these two are generally comparable to each other. But most of the integrated circuit devices for DACs, they use R2R ladder version. This is because R2R is offering a higher precision compared to the binary weighted. And when we consider digital to analog or analog to digital converters, one of the most important thing or the judging criteria is their resolutions, because that resolution is actually giving the more accurate results. So when we consider DAC, let's have a block diagram over here. We have got a set of inputs coming in, D0 to, let's say, D7. Let's put those over there. And we have got an analog output. And for this conversion to perform, we need also the reference current or a reference voltage. And of course, we have got some control inputs, read and write and so on. So this is a typical DAC system. And the important thing about the DAC system, as we already said, their precisions. And that precision is depending on the conversion methods, binary weighted or R2R ladder method. And as we already said, the most majority of the integrated circuits are using R2R ladder version. Now, when we consider these resolutions of the digital to analog converters, the resolution is actually, the output is given, is actually a function of these digital inputs. So the number of data bit inputs it's actually deciding the resolution of that DAC, because the number of analog output levels is equal to the 2 to the power n. So that n is actually our number of inputs, and the number of inputs which will give us 2 to the power n analog output levels, and that actually give us the resolution of that DAC. Now, for example, the most common ones are 8, 10, 12 bits of inputs, or they might have a 16-bit, but it's quite expensive. So when we consider an 8-bit digital to analog converter, in this case we are talking about 256 discrete voltage or current levels. Now, if we are talking about 12-bit one, that means we need 4096 discrete voltage and current levels. So these are actually giving us the resolution of that DAC, and we can easily find out what type of resolution we want, how accurate things we want, and we can use that devices accordingly. So now, when we consider, I'm just going to go to our ladder first. When we consider these circuitries, this is the structure of the R2R ladder. You can find this in any electronic courses. And I'm not going to go into the details of how this is functioning, but generally this is what we have got inside of the DAC. And the typical module that uses R2R ladder is the DAC0808 module. It is an 8-bit digital to analog converter with a 0.9% accuracy and 159 nanosecond settling time. Now, when you consider this device, the digital inputs are converted to current I-out, and we can connect the resistor over to the I-out pin, and we can have the result as a voltage. So the total current provided by the I-out pin is the function of binary numbers from D0 to D7. So this is what is actually provided to us. And we also have the reference current, which must need to be applied as a input current reference and applied to the pin 14, and generally this is 2 milliamps. So we can easily find out the value of the digital bits by using this formula and easily convert it to analog discrete voltage levels. So over here, what we can ideally do is we can connect the output pin I-out to a resistor to convert this current to a voltage and monitor the output on the scope. However, in real life, this is not a really accurate way of doing this, because the input resistance of the load where it is connected will also affect the output voltage. So for this reason, the IRF current output is isolated by connecting it to op-amp with 5K resistor. So that's why we have got this op-amp and the 5K over here, so that we can get rid of that accuracy problem. So I'm just want to do an example for you and how we can convert a digital value to analog, and then we can carry on with the rest of the chapter. So for example, we have got a value 1 0 0 1 1 0 0 1. Now when we consider this number, it's an 8-bit number, so 0 1 2 3 4 5 6 7, that we can say. Now this is 128, and this is 16, that's 8, and that is 1. And all we need to do is we need to add this together. So 128 plus 16 plus 8 plus 1, which will give us 153. Now, as this is a 8-bit digital to analog conversion, we need 2 to the power 8 over there. So 153 divided by 256. Now, that will give us 0.598 as a value. And we know that our IREF we assume that as 2 milliamps for our applications. That means we can convert that value, so 2 times 10 to the power minus 3 by 0.598, which will give us 1.195 milliamps. And then 1.195 milliamps is actually going to be multiplied by with 5K resistor, and this will give us 5.98 volts. So discrete output voltage is calculated. So this is the way of the digital to analog converter is working. Based on the digital inputs that are given, we found the value, then we convert it based on the number of bits that we have. So we'll get 0.598, and then using the reference current, we can easily find out the I out over there. Once we got the I out, as we already have the 5K resistance over there, we multiply that IR and we will get the voltage of 5.98 volts. So this is DAC basics. We are not going to go into the details of that, and we can use this module to convert any digital value to analog using R2R ladder method. And the next thing that we are going to consider in this chapter is the analog comparator. Now, analog comparator in Atmega or AVR is a module that we can get two analog values and compare them. So the positive input is given in AN0 and AN1 is a negative terminal. So when voltage on positive pin is higher than the negative pin, AC0 or ACO bit of ASCR is going to be set. And it's possible to use also the ADC channels as a negative terminals from PA0 to PA7, and we can just use ADC max to configure it, which we are going to see in the later of this chapter. And of course the ACC must be off in this configuration. So with this analog comparator, it's possible to compare 9 analog signals with one positive analog signal, and sequentially but not simultaneously. So we have got a two registers which can configure the analog comparator. One of them is SFIOR. So on that one we have got bit 3, which is ACME, analog comparator maxed enable. So we have to enable the max. In this case, 0 for the IN to be negative input and 1 for ADC of the 8-bit negative analog input. So you can use a multiplexer and select what to compare over there. And the comparator control register gives us the interrupt modes that we can use for ACIS 1 and ACIS 0. So we can use interrupt on toggle, reserved, interrupt on falling edge or on the rising edge. And to enable it, we have to set this bit. And band gap selection, we need to select the band gap voltage reference over there. Analog comparator output with 2 clock cycles of delays. The analog comparator interrupt flags and the interrupt enable to have an interrupt, and input capture modules. They're all configured with the ACSR bits. And the band gap voltage reference. So we have got a internal voltage reference over here that we can use in Atmega 128, and their output is typically 1.23 volts. So the 2.56 volt internal reference is generated from this band gap voltage reference, and we can actually turn this on, or can be enabled when there's a brownout detection, as we have seen in the previous chapters, or the band gap reference is connected to analog comparator. So either this one is set it, or we can just use with the brownout detection. And we just need to be sure that the band gap reference takes up to 70 microseconds to start up and consumes 10 microamps. So it depends on your application that you want to use, but you have to be careful as this is a power consuming module. So that's all that we need to know about the DAC and the analog comparator and the band gap voltage. Okay, now the next thing that we need to consider in this chapter, which is the most important part in this chapter, is analog to digital conversion. Why do we need analog to digital conversion? If you think everything around us in our world, they're all analog. They're not digital. Sound, the heat, the wind, they're all representing an analog signal. So if we want to interact with the outside world, and if we want to measure one of these, what we need to do is we have to get this analog data, we have to convert it to digital and process it. So in order to do that, we need some kind of devices. Now the first thing, or the first equipment or the device that we need, is how are we going to measure those values? So generally, to measure these physical quantities in our everyday life, we need to use transducers. So transducers converts any of these signals into an electrical signal or maybe a mechanical signal. For example, sensor is a input transducer. It converts a process variable, the temperature, the pressure, the wind, or etc., into an electrical signal. Or an actuator, which is an output transducer, it converts an electrical signal to a process parameter. And then what we do, we get these signals and we have to convert them to digital. So we can draw a simple block diagram over here. We have got the sensor, which can be used as an input transducer, and the analog value from that sensor has to get into the analog to digital conversion. We have to convert it to digital so that our CPU can process. Because CPU only understands from zeros and ones, we have to convert it to zeros and ones. And then what we can do, we can display the result. So this is the steps that we need to take care when we are interacting with the outside world, when we want to measure something. And this is known as analog to digital conversion. We need these ADC devices to convert any of these analog signals. For example, we can see different types of sensors that we can use for analog measurements: the position, the force, the temperature, light intensity, maybe the current. So these are all sensors that we can connect to the ADC, and we can interact with the outside world. And it's one of the major areas of embedded systems that it deals with all these sensor values, convert it to digital and process it. Now we are going to see how are we going to use this ADCs with their special characteristics, their parameters, and how are we going to deal with them to configure AVR to perform these operations for us. In AVR, we have got an analog input coming in. We have to specify when to start the conversion, and then we have got an output, binary output value from it. So this is a typical block diagram, with also again with the reference voltage. Now, there are a couple of important parameters and the characteristics that we need to know and understand them carefully before we move on to programming side. And one of these important parameter or the characteristic is the offset. Do you know what offset is? So offset is actually the minimum analog value represented by the digital code. Offset is actually known as Vref minus. So Vref minus in AVR, this is actually 0, is the offset voltage. And when we want to consider the calculations which we are going to do in later of these sections, you are going to see that we need to consider the offset. But when we consider AVR, this is 0. Another important characteristic or the parameter is the span. Span is actually the range. So that range is decided by the Vref positive minus Vref negative. And as in AVR, Vref negative is 0, we will just have Vref as a representation. We can say that Vref is used as the bus reference voltage. So we can actually say that span Vref. Another important characteristic is the resolution. So we have already mentioned in DAC that resolution is important for judging the criterions for the ADC or DAC converters, because resolution is actually telling you the accuracy of the conversion. So the resolution, the ADC has got an n-bit resolution, means n can be 8, 10, 12 or 16-bit resolutions, or even it can be 24 bits resolution. So higher the resolution we have, provides a smaller step size, where the step size is the smallest change that can be discerned by an ADC. For example, 8-bit resolution will have 256 steps, and the step sizes, if we are talking like a Vref as 5 volt, that's going to be 5 over 256, which is 19.53. Or if we have got a 10-bit, let's say, 2 to the power 10, 124 steps, and that 124 steps will actually give us 5 over 124, 4.88. And if you have 12 or 16, we can easily calculate that as well. So although the resolution of ADC chip is decided at the time of the design and cannot be changed, we can control the step size with the help of the reference voltage. So we are going to see an example on this as well. And another important metric is the weight. Weight is actually the analog change corresponding to a change in each bit of the digital code. So weight of the least significant bits is equal to the step size or the resolution itself. The conversion time, so how long will it take to convert from analog to digital, that's also important. And the conversion time is dictated by the clock source connected to the analog to digital conversion, in addition to the method used for the data conversion and technology used in the fabrication of the ADC chip. So there are various things that is affecting the conversion time. And parallel versus serial conversion and the input channels, these are all the characteristics, the major characteristics of analog to digital conversions. As we already mentioned, the VREF is actually an input voltage and used for the referencing. So the voltage connected to this pin along with the resolution of the ADC chip dictates the step size, which we already showed. So if the analog input range needs to be 0 to 4 volts, VREF is connected to 4 volt. That will give us, for an 8-bit ADC, 4 volt divided by 256, 15.62 millivolts for the step size, or for an 8-bit analog to digital conversion. I can give a couple of examples related to that as well. Let's say we have got a VREF which is 5 volts, then in range 5, and the step size is 5 over 256, or 4 volts VREF will have a V in range between 0 to 4, that means 4 over 256, or 3 volts 0 to 3, that means 3 over 256, and these can be calculated. The next thing that we are going to consider is the calculation side of it. So the resolution or the step size can be given by span over 2 to the power n, which we already said, and n is the number of digital bits. We generally use 8, but it can be 10 as well. And this is actually, the span is the VREF, so whatever the VREF is, because we don't have V minus, which is 0. In this case, we just consider VREF itself. And the percent resolution is just the percentage of the resolution that we have found. And the digital output is what we are actually finding out. So when we have the voltage in and the step size, we can easily find out the D out. We might also have the offset. So if we want to consider the offset, we just need to subtract the offset from the input voltage, and then we can find out D out. So let's do an example so that we can understand it better. When we consider an example, it says analog range -5 to +5, digital range 8 bits. So we have got an 8-bit resolution. What are offset, span, step size, and percent resolution and the weights? Let's start with the offset. As we already said, it's VREF minus. So VREF minus, in this case, it's -5 volts. So then span is the range, which is 5 minus 5. It's gonna be 10 volts. And the step size, it's going to be 10 volts divided by 2 to the power 8-bit resolution, which will give us 10 over 256, which is equivalent to 39.1 milliwatts resolution. Now we know the resolution, we know the step size and everything, and the percent resolution is, we just need to take the percentage of that. For the weights, we have got 8 bits, and for the 8 bits, we go from 0, that's going to be, the span is 10 volts, so 10 over to the power 8, which is equals 0.0 0.039, then 1 10 over to the power 7, that's equivalent to 0.078 volts, then 2 10 over to the power 6, which is 0.157 volts, and then third one 10 over to the power 5, 0.313 volts, and it goes like that up to 7. So this is actually showing us the weights of each of them, and it can go up to 5 volts in the end. So for the 7 one, that's going to be 10 over to the power 1, which is equivalent to 5 volts. So this is how we can calculate the weights for it. And the next question is asked, what will be the digital output for the following VINs? Now, there is minus 5 volts, there's a minus 3 volts, 0 volts, and 4.91. Now, if you want to find out the digital out, as we know, the formula for it is D out equals V in minus offset divided by step size. In this case, for the first scenario, V in is minus 5, so that means V out is minus 5. Offset is also 5, and step size is 9.1 milliwatts. This was the resolution that we have already found out. And this is going to be 0 over 39.1 will give us 0. Then we repeat for the other inputs, minus 3 minus 5 divided by 39.1. This will give us 2 over 39.1 milliwatts, which is equivalent to 51. And of course we can write this in hex as 33. Then the next one, which is 0, so 0 minus 5 divided by 39.1, and that will be 5 over 39.1, which is equivalent to 12.8, and it can be x80 when you want to round it. The out is equals 4.961 minus 5 divided by 39.1 milliwatts. So this will be equivalent to 9.961 divided by 39.1 equals 255. In example 2, it says for an 8-bit ADC, we have got a reference voltage of 2.56. Calculate the D0 to D7 output if the analog input is 1.7 volts and 2.1 volts. Before we calculate anything, we just need to first find out the step size, which is equivalent to Vref divided by 2 to the power n. Now, that is going to be 2.56 divided by 2 to the power 8, which is 2.56 divided by 256 in this case, which is equivalent to 10 millivolts. Now, we have got our resolution. The next thing to do to find out the out. So the input is 1.7 divided by 10 millivolts. This is going to be 170. Now, how are we going to represent the 7 down to 0 with 170? So 2 to the power 7, 6, 5, 4, 3, 2, 1, 0. We need 128. That will give us 170 minus 128, 42. Then we need 32. then 10 left. That means we need 8 and 1 over. So in the end we have got 1 0 1 0 1 0 1 0, which will give us 170 as a binary number. Then we repeat for part B. That will be 2.1 divided by 10 millivolts, which is equivalent to 210. And again, D7 down to 0 in a similar manner. 210 minus 128 will give us 82. So 82, then we need 64. That will left us with 18. Then we need 16. 18 minus 16, it will be 2. 048, 044, and then we have got 1 and then 0. So in the end we have got an 8-bit binary values for these conversions. I think this is pretty straightforward. You can try by yourself as well, and if you have any question, please do not hesitate to ask me. Now the next thing that we are going to consider, the analog to digital converters. So analog to digital converters are working as like a sampling data. So over a period of time there's a voltages going on and we are just getting some samples through that period. So voltage input to an ADC is held constant between the samples through a sample and hold circuit. It's just a concept over here where we have got a switch and capacitor, and whenever it turned on, we charge the capacitor. So this is the more practical version of it with the operational amplifiers, and we have got the voltage followers, in this case inputs and output stages with 2 switches, and they have different phases, and this works accordingly. Now the important thing over here, analog to digital conversion is actually using a successive approximation. So what is successive approximation? It's a method of converting analog input to a digital output, and in this case we have got 3 main components in successive approximation, which we can see it from here. We have got the successive approximation register, we have got the comparator, and the control unit. This is like we have got a V-in and V-out coming from the digital to analog converter, and based on that we generate a C-out. So if that C-out is high, that means V-in is greater than V-out. If C-out is low, that means V-in is less than or equal to V-out. Sample and hold circuit samples and stores the analog input V-in. So we have got that V-in analog input. First, for example, we start with 6-bit analog to digital conversion. Set the most significant bit to be 1, and then we compare. So if the digital to analog conversion out is V-in is greater than that output, that means C-out is going to be 1. Otherwise, C-out is going to be 0. And we carry on and we check each bit up until the least significant bit and find out the values over there, 1s and 0s, based on the C-out. So I'm just going to show you an example. This is just showing the steps which I already described over here, but with an example I think it will be much more easier to understand. It says 6-bit analog to digital conversion with V-in is 4.16 volts and the range is 0 to 5 volts. Now, as I start again, step size is equals 5 over 2 to the power 6, which is 5 over 64 in this case, which is equals 0.078. So we have got our resolution as 0.078. And now, when we consider 6 bits, that means 5, 4, 3, 2, 1, 0. The first bit is set to be 1. When the first bit is set to be 1, that gives us a value of 32. So that 32 is going to be multiplied with our resolution, which is 0.078, and this will give us 2.5 volts. Now, this is 2.5 volts and our input is 4.16 volts. So when we compare 4.16 with 2.5, so we can say that 4.16 is greater than 2.5. That means C out is going to be 1. So we leave that one as it is. So we have got the most significant bit to be 1. So that we can freeze that 1 over there. Then we carry on. We add another 1 this time. And we have got, in this case, 32 plus 16 multiplied by 0.078. And this will give us 3.75. By the way, I just rounded that to 0.078. If you want, you can use the exact value on the calculator so that you can have more exact values over here. So 3.75, then that means 4.16 is greater than 3.75, so C out is going to be 1 as well. Again, that means we have to freeze both those. Then we repeat it again, 1, 1, 1, 0, 0, 0. In this case, it's 32 plus 16 plus 8 times 0.078, which is equivalent to 4.375. So in this case, it's greater than, so 4.16 is less than 4.375. That means C out is going to be 0. So we can say that that is going to change to 0. As this is the case, we'll carry on with the next bit, 1, 1, 0. So that's changed to 1, 1, 0 now, because that has to be 0. Then we set the other one to be 1, 0, 0. So 32 plus 16 plus 4 in this case, multiplied by 0.078, which is equivalent to 4.056. Again, 4.16 is greater than 4.056. That means C out is going to be 1. Again, that means we are freezing that one and those, and we carry on with the next bit, 1101, 10 in this case. So 32 plus 16 plus 4 plus 2, that we are multiplying with 0.078, which will give us 4.212, and 4.16 is less than 4.212. That means C out is going to be 0. So that has to be changed to 0. And the last one, 110101, and that is going to be 32 plus 16 plus 4 plus 1 times 0.78, which is equivalent to 4.3134. Again, this is 4.134, so 0.16 is greater than 4.134, so C out is going to be 1 as well. We are frozen that one. So in this case, in the end, we have got 11010, and the last one is going to be 1, and we have got the value as it says. So this will be our result of the operation, 110101, based on the conversion parameters given. And the rest of this slide shows briefly the values that we have calculated on the whiteboard. Okay, so next thing that we need to consider is the linear sensors. Linear sensors means that there's a linear relationship between the measurement and the voltage. So we can draw this like this is our measurement and this is our voltage, and there's a linear relationship between these two. Of course, the slope and the intercept. So what we can say is the analog number is going to be slope multiplied by the measurement plus intercept. So this will give us the analog number. I think the best way to again interpret this is to have an example. Assume that a linear temperature sensor with measurement range minus 10 degrees Celsius to 140 degrees Celsius and output range minus 2.5 volts to plus 5 volts. So we have got the voltage and the temperature ranges. It says if connected to an 8-bit analog to digital converter, find offset, span, step size in both voltage and degrees Celsius. The first step is to write down the offset, which is equivalent to minus 2.5 volts, which is equivalent to minus 10 degrees Celsius, and the span is equals 5 volts minus 2.5 equals 7.5 volts, and this corresponds to 140 degrees minus 10 degrees, which is equals 150 degrees Celsius. So 7.5 volts equivalent to 150 degrees Celsius span. And the resolution is, or the step size, it's 7.5, the span, divided by 2 to the power 8 again, 8-bit resolution that we have got, to 56, which is equivalent to 29 millivolts. 150 degrees divided by 256, which is equivalent to 0.59 degrees Celsius. Okay, so the resolution is 0.59 degrees Celsius or 29 millivolts. So this was the first part of this question. The second part of the question, it says, what is the digital output of the analog to digital converter if the temperature is 10 degrees? So in order to find the digital output of the analog to digital converter, first we have to solve two simultaneous equations to find the linear mapping equation between sensor input and the output. In order to do that, we have got 5 volts, we have got the slope multiplied by with the 140 degrees plus the intercept, and on the other hand we have got minus 2.5, M times minus 10 degrees Celsius plus C. So we can solve these two simultaneous equations, and in the end you can find M as 0.05 volt per degree Celsius and C as minus 2 volts. So these are the two parameters that we were looking for, the slope and the intercept. The linear relationship is as follows. The V out is equals 0.05 times T minus 2. That T is actually the temperature that we are looking for. In this case, voltage for 10 degrees, it's going to be 0.05 volt per degree Celsius times 10 degrees Celsius minus 2 volts, which is equivalent to minus 1.5 volts. And in this case, the digital output, it's going to be minus 1.5 volts minus 2.5 volts divided by 0.029. So this is actually going to give us 34.4, approximately we can say 34, which is equivalent to hex 22. And this is our digital output. If you have any questions related to these, please note them down and you can ask me during the question and answer session. And you can also find the details of these calculations in the slides as well. Okay, signal conditioning. Now, I don't know if you know what signal conditioning is, but it's required in embedded systems as well. Generally, you can see a signal conditioning in electric courses, but in embedded systems, as we are connecting different types of sensors to our system, the important thing over there, as we have got the different sensors, those sensor outputs might not be voltage. They can be microvolts or maybe capacitance or resistance or a current itself. So we need some kind of signal conditioning to convert these to valid voltage level so that the ADC can get these voltage levels and convert it to binary values. So we can say that in many applications the sensor output signal is too small to be accurately converted to digital by analog to digital converter. So signal conditioning, or maybe you can say a voltage converter, it can provide the required amplification and also isolation so that the sensor output does not get modified due to excessive loading. I'm not going to go into the details of this. You can find more details in the electric courses, and all you need to do is you need to understand this. We need a signal conditioning before we do ADC operations if you don't have valid voltage levels. And another important thing that we can go through is the discrete ADC components. So sometimes in embedded systems, or maybe the microcontroller that we are using is not providing efficient, or maybe it's not providing at all the analog to digital conversion. So we can use discrete components and connect them to our microcontrollers. And there are various types of ADCs on the market, but one of the most used and one of the most similar to the AVR's ADC structure is ADC0848, which is an 8-bit analog to digital converter, and their channels are multiplex. It can have an multiple analog inputs, or single-ended or differential modes. And it has got write chip, chip select, and read modes that we have generally with the other types of discrete components. And you can find the more details about it on the datasheet.